Hello everyone, welcome back to a new episode of Advent of Code. I'm starting this one right on the buzzer, so I thought I'd let you guys join me for the countdown. Okay, day 12. Subterranean Sustainability. The year 518 is significantly more underground than your history books implied. Either that, or you've arrived in a vast cavern network under the North Pole. By the way, as you guys can guess, I'm still not doing this for time. If I were, I would not be reading this to you. I could, since I'm, doing this as it releases, but I don't know. That's not why I play Advent of Code. After exploring a little, you discover a long tunnel that contains a row of small pots as far as you can see to your left and right. Okay, sounds like something we're going to want a zipper for. A few of them contain plants. The pots are numbered, 0 in front, and to the left all the negative numbers, to the right all the positive numbers. Your puzzle input contains a list of pots from 0 to the right, and whether they do or do not currently contain a plant. No other pots currently do. Okay. Your puzzle input also contains some notes you find on a nearby table. Someone has been trying to figure out how these plants spread to nearby pots. So this is like a cellular automata kind of thing. That's why okay, yeah, great. Based on the notes, for each generation of plants, a given pot has or does not have a plant based on whether that pot and the two pots on either side of it, okay, had a plant in the last generation. Yeah. And N is whether it will have, okay. So we're going to read a bunch of rules like this that are the rules for advancing time. Okay. Well, if it... Okay. It's not clear what these plants are for, but you're sure it's important. So you'd like to make sure that the current configuration of plants is sustainable by determining what will happen after 20 generations. Okay, so only the ones that do... Input will include all possible combinations. Okay, so that's what, like 2 to the 5th is 32, so it should be 32 line input. The next 20 generations will look like this. And so where is 0 exactly? Ah, I see. This is 0. This is supposed to be 10, 20, 30. And so there's stuff to the left of 0 too, because there are rules about rules that even though nothing to the left of the plants of 0 started with a plant, there's like a rule that says, I guess, let's see. This rule, for example, says if there was nothing here and the 2 directly to the right of you had a plant, then in the next generation here we'll have one. Fine. Generation is shown along the left. Yep. After 1 generation, there's only 7 plants, but then like they start spreading out a bit. Okay. After 20 generations, what is the sum of the numbers of all pots which contain a plant? So this is like the classic example in Haskell. Well, the classic example in functional programming in general that is used to motivate the co-monad class, which is used less often in Haskell than monad is. So when let's take a brief detour to talk about what the deal is with monad and co-monad. So in fact, I won't try to write it down. I'll just okay, so like what is the deal with monad exactly? So monad is a class having return which takes a value and places into the monadic context. And bind, which takes a monadic value and a function that, given a value, produces a new monadic value. And like, so it's sort of like, so if you have, like, for example, lists, you view lists as a monad, where like you look at just a single element at a time, and that element can expand in a way when you use bind into arbitrarily many new elements. Comonad is the opposite. We have, actually this is, I don't even know, I guess it's called, it's probably called something silly like this, I think is what they would call the main operation, which has type like W. I always get confused. So they say that to get comonad, you just take monad and reverse the direction of all the arrows in a way. Now, of course, this is not a legal Haskell type signature. We're just getting there. And they usually spell it W, I think, rather than M. Yeah, so really it's more like, now having reversed the arrows, let's like draw it out. So WB and a function from WB to A, it produces a WA. And now let's like reverse all these, flip the meanings of A and B here. Yeah, so see how it's sort of the opposite? It doesn't take a function which looks at a single thing and produces many things. It takes a function which looks at a big old thing that takes context as input and produces a single value, instead of taking a single value as input and producing a value in a context. And so when applied to lists, this kind of gives you you have like something kind of like, this is something kind of like map, except that instead of only looking at the single value you're mapping over, it can look as far to the left or to the right as it wants and use that. Now, I'm not really a big old expert in comonads. I've like briefly studied them, but I don't like totally get it. And I think that like a great solution to this problem is to go like look up what is the deal with comonad, figure out what library it's in, get the zipper instance for lists. Because a zipper on a list is the comonad instance for lists. And then like read the input to produce a function which has this type, right? We have a function, that's our puzzle input, is a function which, given a value and the values around it, can produce a new value. And so we really ought to implement that. And then our like whole puzzle is just like call extract or whatever the, I think extract is the kind of the opposite of return. It takes a W of A and returns an A. And I forget what they usually call this operation. Insert or something? I don't know. So we could implement that and then just say apply insert 30 times iteratively or whatever. I don't know. That doesn't like sound... That would mostly just be a lot of reading, which is probably like fine, but not really a thing I want to do on camera. So instead, I think that what? I think I will just, well, it's sort of, how do you like project to the left? Because like, I guess we just expand our domain by 2 on each side whenever we have a new generation. How many generations are we doing? 20. That's no problem. Okay. So what even is the type that I want to use to represent one of these rules? It could just be a function that takes like 5 ints and produces, or 5 booleans and produces a boolean. But that kind of like seems lame, doesn't it? Well, no. I want, at the end, a function that takes 5 booleans and produces a boolean. That's like great. But to construct such a function conveniently, it seems like I want to build a tree of bools and then just look up in that. Okay. So, all right. Let's just define a type and like see how that's going to be. Data. Blech. Like, one problem with this type is that I can't very well encode the number, like... The number 5, right? Like, I can build a tree of arbitrary depth, where we have either a branch or a leaf. Fine. But that allows me to, define illegal transition functions. There's sort of this principle that, like, your size, the data structure you use should, in principle, only be able to represent legal values. If there's extra space in your type for, like, things that shouldn't be legal, that's a problem with your type. And likewise, if there's values that should be legal that your type can't represent, that's a different kind of problem. You know, that's why, for example, maybe isn't like just a pair of your thing and Boolean, because like then you could represent nothing in many different ways by specifying false 1, false 2, false 3, false 4. Whereas what you really ought to have is like either true and 1 or false and nothing at all. Anyway. It kind of, I don't know. I guess really all I'm building is a map from tuple of 5 bools to bool. And I can like do it in whatever way I want, but it's not very interesting, is it? Okay, I mean, this kind of feels stupid, but type neighborhood. Well, okay, let's go get our input here. And yeah, observe that it is indeed like... I'm just worried, like, what's part 2 going to be? Is specializing for 5 going to be a problem for me or not? Because what I want to do is, like, say, well, let's say type neighborhood, I guess, of A equals A. 5 A's, right? I don't know. Let's just call it 5. And then we have type rule of A is 5 A's and an A. And then our type transition Do I want to parameterize this by a also, or just take bools? Really, yeah, let's not parameterize it, I guess. Equals m map from 5 A's to a. Oops. Oh, bool. Yeah. So restart Intero here to pull in containers. So we want to build a map of this type, right? And then we have a function that will... We have a neighborhood. Okay, so let's define, I guess, type cell is data cell. I don't know. Data cell. It's just an indexed thing, right? But like, it's a bit. It's a cell of int and we should use a really. So my thinking is it's indexed, right? In fact. So we'll, because we need to actually know the numbers. We can't just produce the bools. That's not sufficient. We need to remember where they are relative to our starting position. Actually. Yeah, this is really not worth giving to regex applicative. It's just too easy. So let's see. What is our input exactly? The input type that I want is a pair containing first, well, both, let's say, a list of index, well, we'll index it after. No. We'll index it first. Indexed bool. And also a transition function, right? I don't know. I keep thinking I should put a type parameter back on transition, but there's really not any reason to. And so parse is function from string to input. So parse of s is let header nothing, oops, it should be colons here. Header cons to nothing cons to rules equal lines of s, right? And then let initial state pots be words of header. and let's say in, let's see. Okay, input of zip width ix of starting with 0 and apply that to map equal hash applied to header. So that's our list of indexed bools. So in fact, let's give this a name as well. Initial init state of rules. And now we need to define rules as well. Rules equal m dot from list of map parse rule of this shouldn't be called rules. Call it transition of rules. Where, well, we'll just define parse rule as a top level function. Parse rule takes a string and produces of course, a rule of bool. Parse rule of s equals case let input nothing output equal words of s in blech. Turning lists and tuples into each other kind of sucks because tuples have a fixed size and lists don't. And here we really it ought to be represented as a tuple because it is limited to 5, but parse rule and words are working with lists, and so there's this kind of point of friction where we have to convert from too large a type into a type that's small enough. So we'll just say A, B, C, D, E. Oh, this should actually be like so, a 5 list in A, B, let's then, I guess, let this be equal to map equal hash of input in A, B, C, D, E. Gosh, we need on, right? Is it function from char to bool? On equals this. This shouldn't... This should also be a list. This is a singleton list. Okay. So let's now try parse of well, let's just say initial state hash dot hash new line dot hash dot. And it won't have a show instance. Very funny. Yeah. Fine. Let's just derive show for this stupid thing. This is the one that needs it. Yeah, so it's an input of a single item. There's... Oh, yeah, where it has... What? Way too many inputs. And then, like, false, true, and a bunch of trues maps to false. That part is correct, right? This part here is correct. What I don't understand is what's going on in the line above it. Why did we fail to parse the initial state correctly? I guess we're looking here, right? Oh, it should have been map on of pots. And this should have been a list, not... We should have been destructuring it as 3 elements, not a list with at least 3 elements. Okay. Now we get initial state is true, false, false, true, which is perfect, and a list, which is our transition function. Great. I guess just in case, let's... Yep, and if we give it another rule, we get another rule back, right? Yes, good. So now all we need is a step function. Step takes a... I guess it takes an input and produces another input, which kind of sucks. Yeah, it does suck. So it should take a transition and then a list of indexed bool and produce another list of indexed bool. Right, which kind of sucks. So what does it do exactly? Like, how do you get a sliding partition of an arbitrary size along a Haskell list? In Clojure, I would use partition 4. Well, 5, I guess. Yeah, 5. With a step of 1. And I know, like, for a list of size, like, if you want to zip together two lists, you have zip with, and that's like pretty okay. And you can zip a sequence with the tail of the sequence itself, and you get, that's fine. And I know there's like zip with 4, zip with 3, zip with 4, zip with 5. They go up to like these ridiculous numbers, and that's kind of fine too. But then I don't know. It's just not really the kind of operation that Haskell wants you to do very badly. Okay, let's leave step alone for a minute and just work on that question. Haskell sliding window of list. Time complexity, I don't really care about that. You can use seek, which has NQ and DQ at both ends. Is that what I want? Maybe. Haskell sliding windows in a tweet. Very clever. Transpose. I see. So in Clojure, we often apply map list over a sequence, and that's how you transpose it. But we don't really have tails. So tails, all right, let's show you guys why this works. Tails of 1, 2, 3, right? Okay, import data list tails transpose. It returns subsequently smaller and smaller chunks of the list, starting at the beginning, dropping 0 elements, then dropping the first element, then dropping the first 2 elements, and so on. So let's put in a few more here. So like, and transpose takes a list of lists and like sort of transposes it as if it were a matrix, dropping excess elements. So if we say transpose take 3 of the tails, well, this is not quite correct. This would be, yeah, I was going to say, don't we lose elements? Now we can take while the list is the right size, and it's fine. All right. So let's define that like window, well, I want this. It's a function taking an int and a list of A and producing a list of A. And that's, again, we're going to lose the information. Like, that's the problem with this, is that what you get back is a type that is too large, right? This type, list of int, can hold all kinds of values that we know are impossible. It could hold a list of 80 elements, even though we said 3, right? And so we want to get this to be a tuple, the right type, as soon as possible. Okay, but fine. We'll define the sliding window thing in general first. Window n x's equals take, wait. I see. His version worked because he passed it an infinite list. take while equal n length on the transpose of take n tails of x's. So now, if we write window 3, we get 1, 2, 3, 2, 3, 4, 3, 4, 5. Okay. So step now of R and x's we need to add more stuff to the outsides of this, which kind of sucks. Last. Okay. I mean, ugh. This is not great. Equals let ix of I and x more equal x's and ix of j, y. Well, let's just I don't want to know anything about any of those. Equal last x's. This again is like bad and I hate it, but okay, now we know the indexes at the beginning and the end. And we'll say next equals ix I minus 2 false. This feels so bad. I minus 1 false plus and then ix of j plus 1 false and ix of j plus 2 false. Okay, so now we have our, like, what we should pretend, we'll call this previous, in fact. This is what the previous generation was, extended out a bit. Neighborhoods equals window 5 previous. No, this is lame. Let's just say in map advance and window 5, where advance of A, B, C, D, E equals R looking up A, B, C, D, E. There you go. Ah. Map. Aha, I knew there was a reason I made index be have a type parameter. Now I can just fmap over it and ignore the index part. That didn't help at all. Yeah, this is totally wrong. Because... Oh, also this is like not actually correct. Is it? Because I actually widened it by 4. I widened it by 2, but I actually need to widen it even more because not only do we need a context for the values that already existed, we need a context for the new values that might come into existence. Okay. Well, clearly we need a function called like stub that takes 2 ints and produces a list of indexed bool. I mean, let's make it take an A and make an index of A. Why not? Stub of from to x equals indexed ix, where I is drawn from up to 2. We call it ix, right? Yeah. So this can now just be stub of I minus 2, I minus 1 of false. And this is, oh, but it shouldn't be minus 2, really. It should be up minus 4. Yeah. And this is stub of yeah, this is okay. Stub of j plus 1 and up to j plus 4 of false. Okay, that wasn't fixing our actual problem, but at least now the list is the right size. My problem is that I want a function that just takes 4 like... Let's see. So window 5 is returning a list of 5 indexed bools, right? And I don't care about the indexes at all. I just want to throw those away, kind of. I don't, though. I need to produce something indexed with C, right? With the index from C. So my thinking, I guess, is it should not quite be this. It should produce an indexed value whose index is ix of C. Let's try this again. Fmap follow rule over C, because C is a single indexed value, and I want to use that thing's index where yeah, I do want another where clause, where follow rule of ix. No, it doesn't take an index. So I don't even want fmap exactly. I want this. Next equals I need to map over the neighborhood and then pattern match it again. Right? Because I want to remove the index from all of these. N prime equals map v over neighborhood. And I guess I want this stinks. God, we should have used a comonet, huh? Is map the neighborhood? No, this makes no sense. Oh, no, that's fine. And next is equal to looking up in R of this. Well, where's this function then? Is it in like data functor apparently? Oh, I'm looking for the other one. I drew it backwards. I don't use this operator very much. I forgot how to spell it. So this thing's type takes an F of... It takes an A and an F of B and returns an F of A. So you take the value and insert it into the functor context, ignoring the value that used to be there. So what's the problem here? No instance for functor indexed. Well, you're right. I didn't say to derive it. Oh my gosh, it compiled. So we recently wrote this, right? So what if I just said to take... That's our initial state. It should map to off, right? Like if I actually run it, if I just say... it's just simpler to, I don't know. Oh, no, don't undo. Put it back. I wanted to undo in this window. Input. It's an input. R... No. Init R equal this. In step R init. Given key is not in the map. Well, that's fair. Oh, sure. Yes, it correctly computed that the leftmost element should be false because this rule matched at the very left and said it should be off, or this rule. But then it tried to match the next one, and like it saw a different thing and blew up. Okay, fine. I'm happy with that. So let's then write. Where's part 1? Part 1 of input init_r equals iterate step of r with init and take the 20th element of that. Let final state equal this. Do I want to do that, or do I need to name another intermediate thing? No, I think I can just in sum of one for, well, actually, length then. Length of, no, it's not, it's neither of those things. It needs to be an actual thing. I, because we want to add up the indexes of these values, right? I for ix of I and v. Actually, I'm going to say true. In final state. Hey, it compiles. So for each entry we find in final state, which correctly matches ix of I and true, we'll just produce I. Is that what we're asked to produce? The sum of the numbers of all pots which do contain a plant. Okay, sure. Let's see what happens. $43.86 seems plausible, I guess. Let's see what Advent of Code has to say about this. That's the right answer. Great. You realize that 20 generations aren't enough. After all, these plants will need to last another 1,500 years to even reach your timeline, not to mention your future. After 50 billion generations, well, we're not going to run that one, right? Huh. How do we, like, what's the shortcut here? We need to learn something interesting. We can't just brute force simulate it. There has to be some closed form solution for like, but even if there were, right? Even if there were a closed form solution, we would still be mapping it over 50 billion integers. And like, that's going to take a while. But we know there must be an efficient solution. Honestly, I have no idea where to start on this one. Like, obviously I could just run this thing for 50 billion iterations, but like it would be too slow. It wouldn't finish. So we're doing like quadratic work, right? For each generation, we do an amount of work proportional to the generation. So even if you could count to 50 billion quickly, which like you can't really, we would have to count to like 10 to the 19th, which is clearly not happening in any realistic time scale. Huh. This is a weird one. I think I'm gonna like not just spend a bunch of time on camera saying huh, and day 12 part 1, and we're just gonna say that we're sort of done for now, and I'll get back to you in the next video and see if I've either figured out something clever here or given up. Thanks for watching, and I'll see you next time.